Let's jump right into this explainer and build a rock-solid understanding of some foundational algebra concepts. We're talking relations, functions, domain, and range. Honestly, these are the absolute building blocks for everything you'll do in higher-level math. It's all about how one thing impacts another.
Moving right into Section 1, Relations, Inputs, and Outputs.
Think about a jetliner changing altitude as it travels, or, a growing kid's weight increasing over time. In both cases, one quantity completely depends on another. Mathematically, we call this a relation. It simply pairs an input value, often called x, with an output value, usually called y. And we generally write these as ordered pairs. Anytime you have a set of these pairs linking inputs to outputs, boom, you've got a relation. It's really just a relationship between two sets of information. Now, when we gather all those possible inputs together into one group, we call that set the domain. And the set of all the resulting outputs, that's the range. It's kind of like a giant machine. The domain is literally everything you are allowed to feed into the machine, and the range is everything that can possibly pop out of it.
But here's where it gets interesting. A relation only graduates to becoming a function if it follows one golden rule: exactly one output per input. If you put a specific x value in, you must know with absolute certainty what the single y value result will be. No guessing, no multiple choice, just exactly one output per input.
Okay, let's pause for a quick check. Take a look at these three ordered pairs. We have 1 paired with 2, 2 paired with 4, and 1 paired with 5. Does this relation follow the golden rule to be a function? Take a second and think about it. The answer is no. Why? Because the input value of 1 is paired with both 2 and 5, which immediately breaks our one output per input rule. I mean, if you input a 1, you wouldn't know if you were supposed to output a 2 or a 5. Because that single input leads to multiple outputs, this relation is definitely not a function.
Okay, Section 2, Tables and Ordered Pairs.
Let's see how this all builds when we organize our data visually. Tables are an incredibly common way to look at relationships because they literally line up our domains and ranges right next to each other. Now, this table brilliantly illustrates a valid function. Every single input on the left leads to exactly one distinct output on the right. An input of 1 gives us 8, an input of 2 gives us 6, an input of 3 gives us 7. See? There is zero confusion and no repeated inputs giving different answers.
Now contrast that with this table. Is this one a function? Nope. Look at the input of 5. It maps to two completely different outputs, 3 and 14. Just like our earlier ordered pairs, if you look down that x column and see the exact same number popping up more than once, you need to check the y column. If those y values are different, the function rule is broken.
Moving on to Section 3, the vertical line test.
Spotting that rule breaker is absolutely crucial, and there's actually a fast visual trick for finding them on a graph. To use the vertical line test, just imagine dropping a perfectly straight vertical line anywhere through your graph. If that vertical line hits the curve or the points more than once, it fails the function test. Why? Well, because hitting it twice means that for that single x input on the horizontal axis, there are two different y outputs.
Let's do our second pause check. Visualize a graph of a perfect circle on a coordinate plane and tell me, does it represent a function? Just picture dropping a vertical line right down the middle of it.
It absolutely does not. A vertical line slices right through a circle at a top point and a bottom point. So that means one single x input has two totally different y outputs. A circle is definitely a relation, but it is not a function.
Here we go, Section 4, Evaluating Function Notation.
Next up, we really need to talk about how we write these mathematically. Instead of always writing y equals, we use notation like f of x to clearly state that an output is a function of a specific input. So, if you're asked to evaluate f of 4 for the function f of x equals 2x plus 3, you just substitute the input 4 for the variable x. That gives you 2 times 4, which is 8, plus 3, giving an output of 11. So when the input is 4, the corresponding output is 11. Simple as that.
All right, Section 5, Domains in Real Contexts. Let's take these abstract inputs and outputs and ground them in the real world. While an algebraic formula might let you plug in literally any number, the real world places boundaries, what we call a reasonable domain. Look at this restaurant context. Say a restaurant is open from 2 p.m. to 2 a.m. and holds a maximum of 200 people. Well, the input, time, is physically limited. The domain is restricted to those 12 hours of operation. from 0 to 12 hours after opening. You can't evaluate the function at hour 14 because the restaurant is closed. Similarly, the range is grounded by reality. The output, the number of clients, cannot fall below 0 or exceed that 200-person capacity limit.
Last part here, Section 6, clearing up misconceptions.
Before we wrap up, we need to completely destroy a few common mistakes 8th graders make with this stuff. First off, remember that repeated outputs are allowed. 5 different students can all get a 3.0 GPA, right? So different inputs can absolutely yield the same output. Second, real-world constraints limit your domain. A context domain is definitely not automatically all real numbers. And finally, those parentheses in f of x, they represent the input of the function. They absolutely do not mean f multiplied by x.
Given a new table of input-output pairs, how would you decide whether it is a function and what are its domain and range?